Hi, everybody, and welcome to this week's episode of Echo Live, brought to you by the Michigan Science Center. Thank you, as always, to Ford and Denso, who have allowed us to continue bringing you all these programs for almost an entire year. Today on this Minisode, we are celebrating Women's History Month. So March is an awesome month, and it's the perfect excuse for all of us here at the Michigan Science Center to celebrate some awesome and amazing women in STEM. Hopefully we have some future women in STEM tuning in. If so, if you are a woman in STEM, if you are anyone who is passionate in STEM, go ahead, introduce yourself in the chat, and let's talk a little bit about what we'll be highlighting during today's episode. Now, if you have the chance to visit the Michigan Science Center this month, we are celebrating Women's History Month all month long with various activities, demonstrations, and even our brand new stage show called Eureka. Now, we are going to spend a little bit of time today talking about nuclear physics. And if you have a chance to visit the Science Center, we are celebrating an amazing woman in STEM. Her name is Dr. Sierra Sibbles. Now, if you happen to follow along with the STEManista project on Facebook or Instagram, you might already know a little bit about Dr. Sibbles. Dr. Sibbles was the first Black woman to graduate from U of M's College of Nuclear Engineering. That is awesome. She is in the field doing the work right now, and she also happens to be one of those scientists featured in the If Then collection. So she is in the field doing the work, but she is also really involved with shaping the future of nuclear engineering. One activity that we have set up here at the Science Center is making pom-pom launchers, talking all about Sierra Sibbles and her job in nuclear physics, talking about this conversion of potential to kinetic energy, and creating one of those pom-pom launchers is just a really simple way to show you that science can be fun, just like it can be important to the future of the world. Now, nuclear science really is the future of energy. And today we're going to learn a little bit about why and how nuclear engineering works. Now, in nuclear engineering and in a fission reactor, which is the type of power plants we use in order to generate nuclear power, we have to set off some sort of chain reaction. And our goal is to harness the energy that comes off of it. One of the easiest demonstrations that you can try at home to talk about chain reactions and the conversion of energy has to do with a set of really simple dominoes. So on this side of my studio table, I have 10 dominoes set up in a straight line. If I input some energy into this system using my finger, I can cause our first domino to fall, which is then going to strike the next domino and the next domino and the next domino in pretty quick succession. So let's take a look at what we mean by a chain reaction. Here we go, 3, 2, 1. Easy enough, right? But in a nuclear plant or in a fission reaction, we're not normally working in a straight line. So on the other side of my table, I've got 2 more reactions set up. And these dominoes are arranged in much more of a web shape, or kind of like a network. If you could see these dominoes from above, they look something like this. So it's the same number of dominoes. I still have 10 dominoes here and 10 dominoes here, but the arrangement is very different. And this helps us to explain nuclear fission. In a fission reaction, we fire one particle that we call a neutron at another atom, something like uranium. When that neutron strikes uranium, it then splits and causes 2 more atoms to be formed, as well as even more of those neutrons, which can go on and they can strike other atoms of uranium. And that what happens is that as that process goes on, we are releasing energy in the form of heat and radiation. So let's take a look at our fission reaction with these 10 dominoes. Here we go. Now you'll notice it wasn't perfect. We need these dominoes to be arranged just perfectly so that these neutrons in the form of dominoes are constantly causing the next domino to fall down. And if this were a nuclear reactor, it would be releasing its energy. So as always, sometimes a diagram can help out with this. But in a fission reaction, like we said, we fire a neutron at an atom like uranium, causes that atom of uranium to start to split into 2, When that happens, we get not just this release of energy, but an exponential increase in the number of neutrons. In the case of this reaction you see behind me, we are releasing 3 additional neutrons, which can then go on and strike a uranium atom of their own, which will then release 3 more, right? So the increase in power is exponential, which is why this form of energy is what is so interesting to scientists like Dr. Civils and other people who are working in nuclear engineering. Now, it sounds pretty dangerous, and it can be, because we have an exponential release of energy and a pretty rapid reaction. If we head back down here to my table, right, we can see that there's a big difference between a straight line chain reaction and this kind of webbed reaction, which simulates our fission reaction in a power plant. So let's set off both of these reactions at the same time. 3, 2, 1. And you might have noticed that this one went a little bit faster. And if there were even more dominoes, this reaction could get quickly out of control. But don't worry, scientists have thought of ways of keeping these reactions safe. Dr. Civils actually works specifically on studying what happens to certain materials when they interact with radiation. Scientists can use what they learn to their advantage because building reactors out of certain materials can actually help us to absorb some of these neutrons. So it limits the reaction and stops it from getting out of control. If you're interested in learning more about nuclear engineering, definitely check out the If Then project. They have even more women who are in the field doing the work right now, women like Dr. Civils and even more. Now I have one last demonstration set up here in the Echo Studio to show you. This is one of my all-time favorite demonstrations of nuclear physics. Down on the floor, so that I couldn't accidentally bump it before we are ready for this demonstration to work, I have 64 ping pong balls and 64 mouse traps. So every single mousetrap has been preloaded before my program, and right now they are storing up that potential energy, that energy that is waiting to be released, much like an atom of uranium, which is waiting to be split once a neutron, another particle, comes in contact with it. So in this case, my neutron is going to be a single tennis ball. So it's a bit heavier, but this will help me to make sure that this reaction at least does detonate. And so I'm going to, very quickly, I'm going to toss my tennis ball down into the reaction, which simulates this first point of contact between the neutron and the atom. So when I drop this down inside, we are going to see all of those mousetraps rapidly release their energy. It's going to fly ping pong balls all over the place, and it should be a pretty cool demonstration all about nuclear physics to celebrate Dr. Civils. So here we go. Our tennis ball is incoming in 3, 2, 1. Oh, and of course it didn't want to work today. Let's go ahead and we'll try it one more time here, very quickly but carefully retrieving my first neutron from our reaction, tossing it back in 3, 2, 1. There we go, a little bit better there. Now, this system doesn't work exactly like a power plant because you'll notice I only have 3 walls. I would really want to have a front wall on this reaction and a ceiling so that all of my neutrons, as they're released from our reaction, and in this case, we're calling our neutrons the ping pong balls, so that all of them get trapped inside. Let's try this again. But you can see that the amount of energy that we release is pretty massive. And just adding in that one neutron sets off a pretty quick and pretty powerful reaction down there inside our container. That's just about all the time we have today for today's Minisode of Echo Live. But one last announcement before we go is that our registration for virtual MySci Spark Camp is open. It's available on our website right now. We are hosting a virtual spring break camp the week of March 29th through April 2nd. If you join us for this week of camp, you will get to experience experiments like this one. You'll get to do them with us live in real time. And you'll get to experience some shows and presentations that you might normally only get if you were to come visit us here at the Michigan Science Center. So our goal is to really bring the Science Center to you and for you to participate in some Echo Live type programs with us, even though you might be at home over this year's spring break. So visit our website to learn more. The registration is open and spaces are limited, so sign up soon. That is all the time we have. I want to say thank you as always for joining us for Echo Live. Thanks for tuning in and watching my mousetrap reactor experiment, and I hope I'll see you all here back